Okay, guys, so in this lab experiment, I'm going to say that this is a pretty staple lab experiment that you would find in an undergraduate science kind of curriculum, and it concerns caffeine. I mean, that's what it is. So we're going to get ready to extract caffeine, and we're going to analyze your caffeine extraction to see how pure this actually really is. So I want to pull up caffeine just for a second so that way you can see some physical properties and some structure of the caffeine molecule. And here you go. It's as easy as that. Just type of a couple of keys on a keyboard, and now I've got all the information that I need. So here is a little bit of background on Wikipedia about caffeine. But more importantly, over here to the right-hand side, you're going to see the structure of caffeine that we're going to be using and dealing with this lab experiment. So a couple of things I want to say about caffeine. First, we do have some ring structures that are here. And, you know, in some of our other labs, we've dealt with these ring structures, but these are not aromatic rings as we've seen before in the past. So we've talked about aromaticity, we've talked about this double single double cause you trouble, but also how those are very appropriate to run on a UV-Vis instrument. And that's really what this lab is about, because caffeine can be ran on a UV-Vis instrument without a problem. So what that means is that this thing probably has some chromophores, and those chromophores are going to help contribute to some absorbance values on our instrumentation. So this works quite nicely in the UV range because a solution of caffeine is colorless, and that will make me kind of pause and say, well, you know, if I've got to put money on it, it's probably going to be in the range of 200 to 400 nanometers, somewhere in there. And it is, and the lab directions are going to tell you to scan it at a certain point so that way you can determine what that maximum wavelength is going to be. In addition to that, because we're running in the UV spectrum, we're going to have to pick out appropriate cuvettes to use for this process, and those cuvettes are going to be our quartz cuvettes. So those are hopefully what we will grab when we get ready to run our samples and our standards on the instrument. So I'll go ahead and tell you that now, because at this point we've probably discussed that a little bit in our lectures, and it's just relating our lecture material to the lab directions that we're getting ready to see. All right, so that means that this molecule is going to absorb some light for me, and that's good. I'm glad that it does, because that's the section that we're in. And I see a lot of these double bond O's. Those very often contribute to UV absorbances. And I also see a lot of nitrogen-containing pieces, and there's a lot of chromophores that have nitrogen that's on the inside. So we've talked a little bit about chromophores. We didn't go into drastic detail, but we at least gave you some examples. And we're like, hey, if any of these flags are on the molecule, then that means it probably is going to do pretty well in the UV range, at least. So as I scroll through, you know, some of the things that we're going to have here as far as physical and chemical properties will be things like molecular weight that you'll be able to get very easily. So 194.194 is the formula weight for caffeine. The density we probably don't have to use. You know, we're going to be measuring out these powders. We're going to be dissolving them in solution, but we're not going to have density for anything. The melting point, maybe, right? So the melting point for caffeine should be around 235 to 238. So I hope that when I extract the caffeine in this lab procedure, one of the ways that we can make sure that it's caffeine is to check the melting point of it. Very easy, very simple process that we can do just to confirm it before we go a little bit further. But as I scroll through, you know, like we've said before in lecture, Wikipedia is going to do a very poor job about giving you lambda maxes and molar absorptivities and those types of things, which are very important for the UV world. So with that said, we've said, okay, well, your resources there, we've got resources for a reason. We've got textbooks for a reason. And that's because in our lab, we have the CRC and we have the Merck, and we have the Sattler. And all three of those are resources that we can use in our laboratory spaces or in the library, and we can look up some pertinent information about caffeine's UV-Vis data. So one of the things that we will need here with caffeine is the molar absorptivity, or the epsilon, right? So we've said depending on which reference book that we look at, that could come to us in the form of the epsilon or E, or it could come to us in the abbreviation of A sub M, where that stands for molar absorptivity, or at least think of it that way, right? Okay, so now that I've kind of teed this up for you a little bit, we need to go through the procedure, and we need to talk about the processes that we're going to have to do before we even get to this point. The processes that we're going to have to do to isolate that caffeine sample, so that way we can clean it up and actually run it on an instrument. So here's a copy of the lab directions. And it looks like this is going to be a very straightforward laboratory procedure. There's really no bells and whistles here. There's nothing fancy going on, nothing complicated. It's just going to be a little bit lengthy as far as involved processes. So it looks like in a 250 ml beaker, I'm going to heat some water, and I'm going to get it close to boiling, but not quite. All right, so that is pretty good, right? So here's my beaker, and I'm just going to put some water in there. Who cares how much? I'm just going to put some in, and it says heat that water up. Then it says add 3 small or 1 family size tea bag. And we're going to swirl it for 5 minutes. So in other words, we're going to brew some tea here. I mean, that's all that we're going to do. So here's my little tea bag. Bloop, there we go. And I'm just going to let it sit out. Let the tea brew. And in that brewing process, what will happen is that I will have caffeine in the tea leaves. And that caffeine is going to go out into the solution. And then that's the solution that we're going to gather and keep and analyze at a certain point. So I'm going to let it do its thing. There's nothing for me to do at that point. I just need to let it sit. Next, we're going to do something that maybe fine tea drinkers will tell you never to do, and that's to take these tea bags and squeeze the bejesus out of them. So what we want is to extract all of that caffeine as much as possible. We're not drinking this caffeine, and very often some people might say, oh, you're not supposed to squeeze the tea bags because it makes it very bitter. Well, I don't really care about that. We're not drinking it. We're trying to isolate the caffeine, and we're trying to get as much of it out as possible. So number 3 is going to say place those tea bags between 2 watch glasses and squeeze them. All right, so the reason that we put them between 2 watch glasses is because it's hot water, and if we put hot water on our hands, it's not going to feel very good. So we're going to take our watch glasses and we're going to squeeze them, and then that will extract some of that caffeine out of there, and we want to collect all of that nice little tea juice that we're getting ready to squeeze out of those bags. Number 4 says, well, you know what, now that you're done with the tea bags, get rid of them, throw them away. We don't need them anymore. And then we're going to cool this solution. And it says if you're really in a hurry, you can put it in an ice bath and you can let it cool very quickly. Or if you're not in a hurry and maybe you're sidetracked and you're doing something else in our lab, that's perfectly okay. Let it cool down to room temperature on its own. Either one will work. Number 5 says, okay, once you've cooled it, I'm going to keep saying that. And the reason is because we're going to pour that into a separatory funnel. And look, it's going to be a quite large separatory funnel here. So that big separatory funnel is going to be used because you probably have quite a bit of water, at least I hope, in that beaker, maybe not full 250 mils, but you've at least filled it halfway, 2/3 full of water when you brewed your tea. Well, we're going to pour that into the separatory funnel, and in the separatory funnel, you know what those look like. We get this kind of teardropped piece of glassware that comes down like this with a stopcock at the end, and we're going to pour our tea juice down on the inside. There it is. And then it says, just be careful. You know, we told you to cool it first, and the reason is because this will build up some warmth, and and we're getting ready to add methylene chloride on the inside. Methylene chloride is MECl2, that's how we abbreviate it, also known as DCM, dichloromethane. It goes by either name, which is perfectly okay, and this has a extremely low boiling point. So what that means is that when I add the DCM into this water layer, I'm going to get two different solutions, and one's going to be water, or the aqueous, and one's going to be the organic, which is my methylene chloride. If the water is too warm, the methylene chloride will evaporate out of there, and if we put a lid on it, we're now going to build up pressure, and if we build up pressure in the separatory funnel and we go down here to the stopcock and open it up, it's going to and it's going to shoot all over the lab, and that's something that I don't want. So make sure it really is cool, because if not, it's going to cause you a problem. All right, so the directions are going to say T-juice in the separatory funnel, and then 20 milliliters of methylene chloride gets added on the inside. You're going to treat this just like you do most of the separatory funnel extractions. You're just going to have to handle this a little more carefully, though. And the reason is because you might set up an emulsion. And an emulsion is this layer that has taken this aqueous and has taken the organic, and it makes it kind of cloudy. It's like an interface layer where it doesn't really fully give you a distinct at least a distinct layer of separation, and that's okay. We're just going to have to be patient a little bit, and we're going to have to let it separate, and we're going to have to let it do its thing, which is not a problem, but it's going to eat away my time if I'm not careful. So 20 mils of DCM goes on the inside, and we're going to rock it back and forth like we normally do. We're going to vent it, and then we're going to keep rocking it back and forth slowly. We're going to vent it, and we're going to do that 2 or 3 times with that 20 mil portion. So we allow these two things to separate, and we're going to drain the DCM layer off, and we're going to capture that into a beaker. All right. Now, I'm not going to tell you which layer is which. You should be able to know this. You'll visually be able to tell this because you've got a whole lot of water and you got 20 mils of methylene chloride. So you'll know which layer is which in the extraction, and that's what this is all about, right? We're not going to baby step you every step along the way. So we're going to drain the DCM off, and I'm going to set it to the side, and the T-juice is going to be in the separatory funnel again, and it says repeat this 3 or 4 more times, which means another 20 mils, rock, shake, separate. Another 20 mils, rock, shake, separate. Another 20 mils, rock, shake, separate. That's what we're doing every portion. That does not mean 20 mils rock shake, add another 20 mils on top of that rock shake. That's not going to do anyone any good. We've already talked about the power of extractions, and we said that smaller portions multiple times very often lead to better results. So when I drain my second portion and my third portion and my fourth portion of DCM, they can actually go back into the same beaker as my first portion of DCM. It's all DCM, folks. That's all it is. It's all DCM. And that's perfectly fine because that's what we need to analyze at some point in time. So what I'm doing is that the DCM here is extracting the caffeine from the water solution. Caffeine dissolves much better in methylene chloride than it does in water. It's a better solvent, so caffeine is going to go into that layer, and that layer is going to capture that organic, and we're going to capture that into the beaker. So another portion of DCM will gather more, and we combine them, and a third portion will gather even more, and we combine them, and you get it. The fourth portion will do the same thing. So it's all about how good of an extraction that I can get, how patient am I, because sooner or later, we're going to have to do a percent yield here, all right? Number 8 says, now that you've got this DCM layer, all right, so now I've got all of these combined portions of DCM, they go back into the separatory funnel, so there it is. And then it says we're going to wash it with 20 milliliters of 6-normal NaOH. All right, so in the separatory funnel, NaOH goes. And NaOH is going to go into the separatory funnel. It's mainly aqueous, right? So just like before, water and organic doesn't mix. We'll see 2 different layers. But what this also means is that that methylene chloride in my separatory funnel that has the caffeine now is going to be hit with sodium hydroxide. And that means I put a cap on it, I shake, rock, separate. That's what I do there. So just as before, I've got a really big volume of methylene chloride at this point, 20, and I've got 20 mils of sodium hydroxide. I'll visually be able to know which one's which. So it says, all right, well, that's your first cleanup stage. So we need to get rid of the NaOH. Ka-cha! Trash it down the sink, into the disposal beaker, wherever we tell you to put it. Just get rid of it. We don't need it. And then it says you're going to do that for a second time. So we're going to do that once, and then we're going to do it again. So another fresh 20 ml portion of 6 normal sodium hydroxide goes in, rock, shake, separate, and then drain that second portion of sodium hydroxide off and get rid of it. There's nothing there that you need. Next, then it says, now we're going to kind of do one more flush of water. So we're going to add 20 mils after that NaOH goes off. We're going to add then 20 mils of water into the methylene chloride layer. Again, water organic doesn't mix. 20 mils of water, a whole lot of DCM. We see separation, rock, shake, separate, and get rid of that 20 mils of water. That is not what you need. Everything that you were after is still in the methylene chloride layer. What we're doing here with the sodium hydroxide and the water, I want you to think of as a cleanup stage. Not everything is just caffeine in the methylene chloride. The methylene chloride is an organic solvent, and it will bring with it many things. Caffeine is one of them. So we're just trying to get rid of some of these extraneous little things that are coming along for the ride. So the sodium hydroxide and the water is going to help that cleanup process to happen. All right. Note number 9 says now this methylene chloride should be a very clear solution. So you should be able to see through it. It shouldn't be cloudy. It might be a tinge of color, and if so, that's okay, but you should at least be able to see through it without a problem. It says if you don't, then we can add a little bit of drying agent. We can allow that water absorption to take place before we go further, because that can cause us a problem if we're not careful. We also have, instead of drying agent, we also have some phase transfer paper. And the phase transfer paper will actually allow all organics to go through, so the methylene chloride will be able to go through without a problem, and it holds or retains behind any type of water that might be still in your solution. So think of this as like a filter paper, but a specialized piece of filter paper that can separate the water from the organics. Next, number 10 says now we're going to weigh, ding, 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 a 100 mil volumetric flask, or I mean a round bottom flask, because we need to evaporate this methylene chloride off now. And we're going to have this residual residue that's left behind, and that residue is going to be caffeine. So I hope that it's going to be kind of whitish or beigeish in color, and it's going to be powder that I can visually see with my eyeballs, because that means that I've did my extraction pretty well, if that's the case. So I'm going to weigh a 100 mil round bottom, and then it says transfer all of that methylene chloride solution that now has your caffeine, pour all of that into the round bottom, and then we're going to use a simple pot distillation or a rotary evaporator here. Rotary evaporators we actually have ready to go in our lab. They're probably going to be the most convenient. So we're going to slap our methylene chloride and our round bottom flask onto those rotary evaporators, and we're going to allow the rotary to do its job. And that's to slightly heat this sample up, get rid of the solvent, and now we're going to have a round bottom flask that has all of this little crystal crud that's on the inside, and that is going to be my caffeine. Next, it says, well, that round bottom is probably going to be a little warm, so we're going to have to let it cool. So we're going to put it in a desiccator, because the whole idea here is, make sure there's no water absorption. We don't want water weight. So put it in a desiccator, allow it to cool in the desiccator, and then go back 20 or 30 minutes later, and then we're going to take a mass of it again. All right, so we're going to take the mass of it clean, and then we're going to have the mass of it with stuff, and we're going to subtract those two values together, of course. And that will allow me to get the grams of caffeine that we have extracted from the lab procedure. Now, I know that this is a crude product, right? We didn't do any type of purification here. We did one extraction, and that extraction got hit into a separatory funnel with some different solvents, but we did not fully go through like a recrystallization process. The directions are actually not going to tell you to do that at all. So this gram here is a crude gram of caffeine, and we are going into this with the assumption that this is not pure, and that's okay, because that is the purpose of the UV-Vis instrument that we're going to be running with our sample. So after we weigh it, we cool it, then weigh it, and then we'll get the grams of caffeine that I have in my container. All right. Number 16 says, determine the percent of extraction. Well, what this means is that you actually can use Google, right, or some type of website that will tell you the typical amount of milligrams of caffeine in a serving size of tea. So what that means is that go to our box that we bring into the lab. Sometimes the box will have the milligram amount stamped on the serving size, and it will tell you 1 tea bag is equivalent to this many milligrams of caffeine. So if we have brought in a box like that, make sure that you get that number off of there, because you will need that value sooner or later. Just keep in mind, the directions are going to say if you take the tiny tea bags, take maybe 3 of those. Whatever's stamped on the box is typically 1 tea bag. So you're going to have to multiply that by 3 if that's what you've used, because that will be your theory amount of caffeine from 3 tea bags, not 1, right? So keep that in mind. Serving size is typically 1 tea bag if it's a personal size tea bag. All right, so that will give you the target amount of caffeine that you should have isolated. And what we hope is that your value gets really close to that. So it might not, I don't know, but I'll keep my fingers crossed for you, because sooner or later you will have to plug that into a spreadsheet that looks something like this. All right, so when you bring up this template, what you will see is 2 tabs on the spreadsheet template, and here is our extraction tab down at the bottom. And here we see the mass of the bowling flask, so that's where I would key that in. And here's the mass of the bowling flask and the product. So that is how much maybe this thing weighs after I see my little white solid crud that I'm going to assume is caffeine in the bowling flask. All right, so after that, we take these 2 masses and we subtract them. So that will give me the gram amount of caffeine that I have that I get to work with at this point. And for this person, it was a very tiny amount. So grams to milligrams, they did that conversion, and it looks like 60 milligrams from 3 tea bags. That's not a lot, folks. I mean, very, very low recovery here. So I hope that your number is going to be better than that. But we'll see, and you'll see that when you get into the lab. So don't rush those extraction processes, because that's really going to make or break your amount here that you'll end up in the very end. Okay. Then after that, we're going to let it dry. We're going to come back on a different day. We're going to do a melting point of it. And by doing a melting point, we're going to lose some of that mass, right? And that's what you're going to see down here at the very bottom. So here in this section, you're going to see that after the MP analysis, we are going to reweigh that bowling flask with crude product in it. And the purpose of that is because I know, again, I've used some of that to do a melting point of. So what do I have left over now? And if you look at this, the mass of the flask after the melting point was 67.811 for this person. So when they took that mass and now subtracted it from the original, what they're going to end up seeing is that their mass went down, and it should. So now they're working with 51 milligrams instead of 60 milligrams. So this seems like they used 9 or 10 milligrams for our melting point system to do a proper melting point of. And that is what's left over that we get to use for Part B. So don't forget to correct for that step. The lab directions are going to actually walk you through that and remind you of that so you don't forget it. but that correction has to be made in order to go into part B of the lab experiment. If you get a little bit lazy with the particulars of the caffeine UV data, here's the molecular weight for caffeine, the melting point of 238, the density of 1.23. The lambda max here is 273 for caffeine once and if you find it in a reference book, and the molar absorptivity for caffeine is going to be 8510. So we will need those values sooner or later in order to do some of these calculations for part B when it concerns UV. But now, I mean, there's your reference points. As far as the melting points go, you'll see a little block that's going to be here. This is your product melting point. So this person got 238. And then the pure caffeine, this is caffeine from stock. So we have ordered caffeine. We've tried to get the highest purity that we can without going crazy with it. And when that person ran that melting point, they received 229 Celsius as the melting point for that. So that way they can compare how close is mine to the stock that was actually ordered. All right. Okay, so that is where we will end this lab experiment discussion. In part 2, we will go through and we will talk about this whole idea or concept of what we need to do on the UV side of the house. So in that video, we'll go into more details about standard prep, sample prep, and some UV settings that we need to go through. All right, so I'll see you in the next video. This will give you a head start. See you later.